What if I told you that some of the most advanced tools ever created weren't made in Silicon Valley or modern laboratories, but thousands of years ago by civilizations we often underestimate? Picture a Roman architect mixing concrete so durable it still stands strong after 2 millennia, while our modern buildings crumble after just decades. Think about a blade forged in ancient Damascus, its edge so precise it could split a hair lengthwise, something even today's finest surgical steel struggles to achieve. These aren't myths or exaggerations. They're real, tangible proof that our ancestors possessed knowledge we're still scrambling to rediscover. This video is a journey back in time to uncover 30 astonishing inventions from the ancient world, tools and technologies so brilliantly designed, they put our modern equivalents to shame. We're not just talking about simple gadgets or lucky accidents. These were masterpieces of engineering, crafted with an understanding of materials and physics that seems almost supernatural. How did the Egyptians drill granite with pinpoint accuracy using nothing but copper and sand? Why did Greek fire burn uncontrollably, even on water, while our best flame retardants fail under far less pressure? The answers lie in a forgotten era of innovation, where necessity didn't just breed invention, it perfected it. But here's the real mystery. Why did so many of these breakthroughs vanish for centuries, only to be reinvented or never fully replicated in modern times? Was it war, secrecy, or simply the passage of knowledge slipping through the cracks of history? As we explore these ancient marvels, you'll start to see a pattern, a thread connecting craftsmanship, ingenuity, and a deep respect for natural materials that our disposable, mass-produced world has largely forgotten. By the end, you won't just admire these tools, you'll wonder what else we've lost and what that means for our future. So let's dive in, because the past has surprises that just might change how you see progress forever. Buried beneath the waves for over 2,000 years, the Antikythera Mechanism wasn't just another artifact, it was a revelation. When divers first pulled this corroded bronze object from a shipwreck near Greece in 1901, they assumed it was a simple navigational tool. But decades later, X-rays revealed something extraordinary. Dozens of interlocking gears, precisely arranged to track the movements of the sun, moon, and planets. This wasn't just a clock or a calendar. It was a mechanical cosmos, a miniature universe inside a shoebox-sized device, capable of predicting eclipses down to the hour and even accounting for the irregular orbit of the moon. The genius of its design lies in the subtlety of its engineering. Unlike modern computers that rely on electricity and silicon, this ancient Greek marvel used nothing but hand-cut bronze gears, some with teeth so tiny they resembled the edge of a coin. Each gear was a mathematical equation in physical form, turning in perfect harmony to replicate the celestial dance above. The device even included a dial to forecast the Olympic Games, proving its creators saw no boundary between science, sport, and the stars. Yet here's what stumps researchers today. We've built replicas with laser precision and computer modeling, but none operate as smoothly as the original. Modern engineers suspect the Greeks employed techniques we've yet to fully understand, perhaps a lost method of alloying bronze to reduce friction, or a deeper grasp of planetary physics than we've credited them with. Some gears in the mechanism correspond to cycles we didn't rediscover until the Renaissance, like the Saros cycle for eclipses. How did they know? The answer might lie in a lineage of knowledge stretching back even further, to Babylon's star-charting priests or Egypt's temple astronomers. What's truly humbling is realizing this device wasn't a one-off experiment. Cicero wrote of similar machines in his time, suggesting the Antikythera Mechanism was just one of many, a glimpse into a Hellenistic world where science and art were inseparable. Today, we swipe screens to check moon phases, while 2 millennia ago, scholars turned handcrafted gears to unlock the secrets of the universe. The question isn't just how they built it. It's why we ever stopped. The Pantheon in Rome has stood under the same unreinforced concrete dome for nearly 2,000 years, through earthquakes, wars, and the slow erosion of time. Meanwhile, modern concrete bridges and parking garages often show cracks within decades, sometimes collapsing entirely after just 50 years. What made Roman concrete so indestructible? The answer lies not in superior technology, but in a forgotten alchemy of nature and human ingenuity. Ancient builders mixed volcanic ash from the region of Pozzuoli with lime and seawater, creating a chemical reaction modern scientists call pozzolanic. This wasn't just strong, it was alive. When tiny cracks form in Roman concrete, seawater seeping in reacts with the volcanic material to grow new mineral crystals, effectively healing the damage. Imagine a skyscraper that repairs its own fractures after an earthquake. That's not futuristic fantasy, it was reality in the 1st century. Modern engineers only cracked the code in the last decade. Laboratories analyzing drilled cores from Roman harbors found interlocking minerals like stretlingite and aluminum tobamorite rare formations that strengthen over time. Our concrete, by contrast, relies on steel reinforcements that rust or Portland cement that shrinks and fractures as it cures. The irony: we've been using volcanic ash in concrete since the 1920s, but never in the precise ratios or with the saltwater curing process the Romans perfected. The most baffling part: this knowledge wasn't lost to some catastrophic event. Vitruvius, the famed Roman architect, literally wrote the book on concrete mixing in the 1st century BC. His detailed recipes were ignored for centuries as construction shifted toward cheaper, faster methods. Today, researchers from MIT to the University of Utah are reverse engineering these ancient mixes, hoping to create seawalls that withstand rising oceans or nuclear waste containment that lasts millennia. Perhaps the real lesson isn't just about chemistry, but philosophy. The Romans built for eternity, choosing materials that matured like fine wine. We build for deadlines, trading longevity for short-term efficiency. Walking through the Pantheon's soaring dome, still the world's largest unreinforced concrete structure, you can't help but wonder, if we relearned their patience, what could we create? When a Damascus steel blade first caught sunlight on a medieval battlefield, it wasn't just a weapon, it was a masterpiece. These legendary swords, wielded by crusaders and sultans alike, could slice through armor while bending like a willow branch without breaking. Their surfaces shimmered with watery patterns, as if forged from liquid metal frozen mid-ripple. But what truly set them apart wasn't their beauty. It was their impossible combination of hardness and flexibility, a paradox modern metallurgy still struggles to replicate. The secret lay in the raw material, Wootz steel, a rare ingot smelted from iron ore mined in India's Deccan Plateau. Ancient blacksmiths heated this ore with specific leaves and wood bark, infusing the metal with carbon in precise amounts. Then came the magic, repeated folding and hammering at exact temperatures, sometimes over dozens of layers. This wasn't random pounding, it was a carefully choreographed dance between fire and force, aligning microscopic carbide structures into waves of ultra-hard steel separated by softer, flexible iron. The result, a blade that could hold an edge sharper than a surgeon's scalpel yet absorb brutal impacts without shattering. Modern scientists have spent decades trying to crack the code. Electron microscopes revealed nanowires of carbon nanotubes in authentic Damascus steel, structures we only learned to synthesize in labs in the 1990s. Some theories suggest trace elements like vanadium or tungsten in the original ore played a role, while others point to the unique quenching process, where blades were cooled in exotic mediums like dragon's blood, likely a coded term for plant sap or animal urine. The closest modern equivalent, pattern-welded steel, mimics the visual effect but lacks the legendary performance. Even today's high-tech powdered metallurgy can't match the self-sharpening edge of a true Damascus sword, where wear would expose fresh layers of hardened steel beneath. Perhaps the most haunting clue lies in timing. The finest Damascus blades appeared between the 3rd and 17th centuries, then abruptly declined in quality. Some historians blame exhausted minds, while others suspect guilds lost their proprietary techniques to war or secrecy. But here's the twist. When researchers analyzed a 17th century Persian manuscript describing the process, they found instructions so precise that following them today produces blades eerily close to the originals. This wasn't lost knowledge, it was ignored knowledge, buried under centuries of industrialization's rush toward faster, cheaper production. Holding a genuine Damascus sword today feels like touching a ghost. The metal seems alive, its patterns shifting under light as if whispering secrets we've yet to fully hear. In an age where we can 3D print titanium, it's humbling to admit that a 1,000-year-old blade still outclasses our best. Maybe the real question isn't how they made Damascus steel, but why we ever settled for anything less. Imagine a weapon so terrifying that seeing its flames strike the water could make entire fleets retreat in panic. Greek fire wasn't just another tool of war. It was the 7th century equivalent of a superweapon, a liquid nightmare that clung to ships, burned on waves, and couldn't be extinguished by anything the enemy tried. Byzantine sailors would unleash it through bronze tubes mounted on their ships, spraying jets of fire that twisted and danced across the sea like a living creature. Historical accounts describe its glow illuminating nighttime battles, with screams of sailors trapped in flames echoing across the water. What made Greek fire so uniquely devastating? The answer lies in its chemistry, a recipe so closely guarded that even today we can only guess at its ingredients. The Byzantine emperors treated the formula as a state secret, known only to a handful of trusted alchemists and the ruling family. Modern researchers have pieced together clues from fragmented texts and battlefield reports. Some believe it contained distilled petroleum, similar to modern napalm, mixed with pine resin for stickiness and quicklime to ignite on contact with water. Others speculate about secret additives like sulfur or saltpeter, giving it self-sustaining flames that defied ordinary methods of dousing. The true genius of Greek fire wasn't just its flammability, it was its delivery system. Byzantine engineers designed pressurized bronze siphons, essentially ancient flamethrowers, capable of projecting the liquid fire in precise arcs. These weren't crude torches, they were technological marvels, likely using hand pumps and preheated compartments to maintain consistent pressure during battle. Historical records mention a deafening roar accompanying each burst, suggesting the mixture may have ignited explosively as it left the nozzle. Here's what baffles historians. Despite countless attempts, no modern reconstruction has fully replicated Greek fire's legendary properties. Laboratories have created mixtures that burn on water, but none match the descriptions of its uncontrollable spread or the way it reportedly ignited even on soaked wood. Some theories suggest the Byzantines exploited natural petroleum seeps with unique chemical properties, now lost or depleted. Others propose that the real secret wasn't just the fuel, but a specialized ignition system, perhaps involving hidden sparks or reactive metals embedded in the siphon nozzles. The weapon's psychological impact was as potent as its flames. Enemy ships would scatter at the sight of Byzantine dromons approaching, knowing a single hit could doom an entire crew. Its mere existence may have delayed the fall of Constantinople for centuries, as invaders feared facing this unholy fire. Yet by the 15th century, the knowledge vanished, possibly lost when secretive guilds dissolved or during the empire's final collapse. Today, Greek fire remains one of history's most tantalizing mysteries, not just for its destructive power, but for what it represents, a glimpse of ancient science pushed to its limits, where chemistry and warfare merged into something both brilliant and terrifying. In an age of nuclear weapons and drone strikes, there's something haunting about a liquid flame that still outburns our best attempts to understand it. Deep inside the pyramids and temples of ancient Egypt, you'll find holes drilled into solid granite so precise they look machine-made, yet they were created over 4,000 years ago, long before electricity or modern tools. These aren't rough gouges or jagged openings. They're smooth, cylindrical passages, sometimes stretching several inches deep, with spiraling grooves so consistent they could pass for factory work. How did a civilization without hardened steel or power tools achieve this? The answer lies in a deceptively simple combination: copper tubes, quartz sand, and patience sharper than any laser. Egyptian craftsmen used hollow copper drills, twirled by hand or with bow-like devices, to carve through stone harder than the drill itself. Here's the brilliance: they didn't rely on the copper to cut the granite. Instead, they packed the drill's tip with wet sand, a humble material hiding a secret weapon. Sand contains quartz, one of nature's hardest minerals. As the copper tube spun, the sand grains embedded themselves into the softer metal, creating a makeshift abrasive surface tougher than the granite. Each rotation ground away microscopic particles, while water kept the process cool and flushed out debris. Over hours or days, this slow-motion dance of friction and persistence yielded holes with tolerances that still impress engineers today. Modern experiments reveal just how advanced this method was. When researchers tried replicating Egyptian drilling with period-accurate tools, they found the spiral grooves inside the holes matched the theoretical feed rate of quartz particles. Proof the ancient workers understood abrasive mechanics at an intuitive level. Even more startling, some granite cores extracted from these holes show feed rates of under 2 millimeters per minute, meaning craftsmen maintained perfect pressure and alignment for impossibly long stretches. Today, diamond-tipped drills wobble at such fine tolerances, yet Egyptian holes remain straight over depths that would challenge our best CNC machines. The real mystery isn't just how they drilled, but why we've found granite fragments with drill marks suggesting speeds of over 1,000 revolutions per minute. No human-powered bow drill could achieve that, leading some researchers to speculate about lost mechanical aids, perhaps pulley systems or even primitive rotary tools powered by teams of workers. Other enigmas linger. How do they keep drills perfectly perpendicular without modern levels or guides? Why do some holes taper at exact, repeatable angles? The deeper you look, the clearer it becomes this wasn't trial and error. It was applied physics, mastered centuries before the scientific method existed. Perhaps the most humbling detail lies in the unfinished artifacts. A broken drill core still lodged in a granite block at Aswan reveals something extraordinary. The Egyptians drilled from both ends, meeting precisely in the middle. That's alignment accurate to within fractions of a millimeter across several feet of solid stone. Even with laser guidance, we'd struggle to match that today. Walking through the temples of Karnak or running a finger along those ancient drill marks, you're touching more than stone. You're touching a legacy of craftsmanship so refined, it silently questions what we call progress. In the year 132, a Chinese astronomer named Zhang Heng unveiled a device that seemed to defy logic, a bronze vessel adorned with dragon heads, each clutching a metal ball. When the earth trembled hundreds of miles away, one of those dragons would open its jaws, dropping its ball into the waiting mouth of a bronze toad below with a resonant clang. This wasn't magic, it was the world's first seismoscope, a machine so elegantly designed it could pinpoint the direction of distant earthquakes while officials in the capital still felt nothing. The genius of Zhang Heng's invention lay in its deceptive simplicity. Inside the ornate vessel hung a delicate pendulum, suspended like a plumb line. When seismic waves arrived, even faint ones traveling through bedrock, the pendulum would sway, striking one of 8 lever arms arranged like compass points. Each arm connected to a dragon's head on the corresponding side of the vessel, releasing only the ball aligned with the quake's origin. Historical records describe it detecting a quake in western China from the capital city of Luoyang, days before messengers arrived with news of the devastation. Modern engineers have spent decades reconstructing how it worked. Some theories suggest the pendulum was weighted to respond to specific wave frequencies, filtering out local vibrations like passing carts or footsteps. Others propose the lever system amplified tiny movements with precision worthy of a Swiss watchmaker. The most startling revelation: replicas built using Zhang Heng's descriptions can detect quakes as effectively as early 20th century seismographs despite having no electronics or moving parts beyond the pendulum. What truly sets this ancient device apart is its philosophy. Today's seismographs produce squiggly lines on paper or screens, requiring experts to interpret them. Zhang Heng's design communicated instantly and intuitively. A ringing bronze ball told officials not just that the earth had moved, but where to send aid. In an era without telegraphs or radios, this was life-saving technology. Yet the most haunting question isn't how the seismoscope worked. It's why its principles were forgotten for centuries. The original was lost to time, possibly melted down for its bronze, and later Chinese dynasties dismissed it as superstition. Western science wouldn't develop functional seismographs until the 1800s, nearly 2 millennia later. Walking through modern earthquake monitoring centers filled with blinking servers, you can't help but marvel at how much quieter and perhaps less poetic our warnings have become. A dragon's silent vigil replaced by digital alerts. Facing the open ocean under thick clouds, Viking navigators had no compasses, no stars, and no visible horizon, yet they crossed thousands of miles of treacherous seas with pinpoint accuracy. Their secret, a seemingly ordinary crystal that could reveal the sun's position even on the gloomiest days. These sunstones, mentioned in medieval sagas and later identified as calcite crystals, weren't just tools. They were nature's own GPS, harnessing light in ways science only recently understood. Holding a calcite sunstone to the sky, Viking sailors would rotate it slowly until something extraordinary happened. The crystal's unique property, called birefringence, split incoming light into 2 beams. By turning the stone until these beams matched in brightness, they could pinpoint the sun's hidden location with startling precision. Modern experiments prove it works. Even when clouds obscure the sun entirely, this method determines its position within 5 degrees. That's accurate enough to sail from Norway to Greenland without veering off course, guided by nothing but a rock and keen observation. What's truly remarkable is how little the Vikings needed. Unlike modern navigation, which depends on satellites vulnerable to solar flares or hacking, sunstones required no infrastructure, just an understanding of light's behavior. Researchers suspect Vikings combined them with other natural cues, like the direction of waves or migratory birds, creating a layered navigation system as reliable as it was portable. A 2012 discovery cemented this theory. archaeologists found a calcite crystal aboard a 16th century shipwreck, perfectly preserved near the captain's navigational tools, the first physical proof of sunstone use. Today's military and survival experts still study these crystals. French scientists demonstrated that sunstones can track the sun up to 7 minutes after sunset, while pilots in polar regions where compasses fail have tested them as emergency backups. The irony: we've spent billions developing satellite networks, yet in some conditions a piece of calcite outperforms them. The deeper lesson lies in the Vikings' relationship with their environment. They didn't conquer the North Atlantic by brute force, but by listening to nature's subtle signals, a philosophy modern technology often overlooks. Standing on a foggy shore with a sunstone, you realize something profound. Sometimes the most advanced tool isn't the one with the most components, but the one that teaches us to see the world differently. High in the Andes, where earthquakes shake the ground like a drumskin, stand walls built by the Inca that have defied centuries of tremors without a single crack. These aren't just stacked stones, they're three-dimensional puzzles, each block cut with such precision that even today, you can't slide a razor blade between them. Modern engineers have scanned these joints with lasers and found gaps smaller than 0.5 millimeter, a tolerance that would challenge our best diamond-cutting tools. How did a civilization without iron tools or the wheel achieve this? The answer lies in a marriage of patience, geology, and genius-level understanding of seismic forces. The Inca didn't just cut stones to fit, they shaped them to dance. Unlike our rigid concrete structures that crack under stress, Inca walls use a technique called ashlar masonry, where each stone is slightly convex on its outer face. When an earthquake strikes, the stones in the wall shift and settle, then snap back into place like a self-healing mosaic. Some corners feature stones with 12 or more angles, interlocking like gears to redistribute energy. The most astonishing examples, like the 12-sided stone in Cusco's Hatenrumayok Street, show blocks with undulating edges that seem to defy logic. No straight edges, yet every curve mates perfectly with its neighbor. Modern scientists have tested these designs using shake tables that simulate quakes. While contemporary brick walls crumble at magnitude 7, Inca-style replicas remain standing at magnitudes over 9. The secret: friction and flexibility. The irregular shapes create thousands of micro-contact points that absorb vibrations, while the lack of mortar allows subtle movement without catastrophic failure. Today's earthquake-proof buildings use expensive steel frames or base isolators, yet the Inca achieved better results with nothing but stone-on-stone craftsmanship. Perhaps the most humbling detail is how they worked the stone. Researchers experimenting with Inca techniques found that workers likely used harder stones to pound and shape granite and andesite, gradually refining surfaces by trial fitting, a process that could take months for a single block. Some theorize they used sand or clay molds to transfer complex shapes between stones, like prehistoric carbon paper. Others point to the mysterious llama's blood, mentioned in colonial texts, possibly a plant-based lubricant that helped polish surfaces to that impossible smoothness. But here's what truly stuns architects. These weren't just royal monuments. Ordinary storehouses and terraces built with the same care still stand after 500 years of quakes, while our reinforced concrete schools and hospitals need rebuilding every few decades. Walking through Sacsayhuaman or Ollantaytambo, you're witnessing more than ruins. You're seeing a masterclass in sustainable engineering, where every chisel mark was a conversation between human hands and tectonic forces. The stones whisper a question we've yet to answer. If building to last was possible then, why isn't it our standard now? In the scorching deserts of ancient Persia, architects confronted a challenge that still plagues us today: how to stay cool without draining precious resources. Their solution, towers that rose like silent sentinels above clay rooftops, channeling desert breezes into homes with the efficiency of a modern air conditioner, yet using no electricity whatsoever. These windcatchers, or badgers, weren't just decorative. They were masterpieces of passive cooling, turning blistering summer heat into refreshing drafts through pure physics. The genius of the windcatcher lies in its marriage of simplicity and sophistication. Each tower was strategically oriented to catch prevailing winds, funneling them downward through vertical shafts. But here's where the real magic happened. At the base of these shafts, air passed over underground water channels or moist clay pots, triggering evaporation, nature's oldest cooling trick. The resulting drop in temperature could chill interior spaces by up to 20 degrees Fahrenheit, all while wind pressure forced stale air out through opposite-facing vents. Some larger windcatchers even featured multiple openings to capture breezes from any direction, adjusting to shifting desert winds like a natural thermostat. Modern engineers have measured their performance with digital sensors, and the results are staggering. A single windcatcher can circulate over 12,000 cubic feet of air per hour, enough to cool a medium-sized house with zero carbon footprint. Compare that to today's air conditioners, which guzzle nearly 10% of global electricity and leak potent greenhouse gases. The irony: contemporary, green buildings now incorporate windcatcher-inspired designs, from London's iconic Gherkin skyscraper to Dubai's sustainable neighborhoods, proving this ancient tech still outshines our energy-hungry alternatives. What's truly remarkable is how windcatchers adapted to their environment. In coastal regions like Iran's Keshem Island, they were built wide and squat to harness humid sea breezes, while desert versions soared tall to catch dry, fast-moving winds. Some even incorporated ice chambers in winter, storing cold to combat summer heat, a prehistoric version of thermal mass storage. The finest examples, like those in Yazd, still function flawlessly after 800 years, their wooden latticework directing airflow with the precision of a Swiss watch. Yet the most humbling lesson isn't in their engineering, it's in their philosophy. Persian builders worked with nature rather than against it, using materials like mud brick that actually improved with age as salts crystallized to strengthen walls. Their cooling towers required no moving parts, no fossil fuels, just an intimate understanding of wind patterns and water's transformative power. Standing beneath one today, feeling that steady stream of cool desert air, you realize something profound. Sometimes, the most advanced solution isn't about inventing new technologies, but remembering old ones we shouldn't have forgotten. While modern highways crumble under the weight of trucks and weather, some Roman roads still carry traffic after 2,000 years, not as museum pieces but as functional thoroughfares. The Via Appia, begun in 312 BC, stretches like a stone ribbon across Italy, its original sections so durable they've outlasted empires. What made these ancient highways so indestructible? The answer lies in a construction method so meticulous, it puts our modern asphalt to shame. Roman engineers treated road building like crafting a layered cake, each stratum serving a precise purpose. First, they dug trenches up to 5 feet deep, reaching stable ground. Then came the statumen, a base of large stones set in mortar, designed to displace weight and prevent sinking. Above that, the rudis, a mix of rubble and lime, acted as a shock absorber, while the nucleus layer of sand or gravel allowed subtle flexing, the crowning glory. Summa crusta, interlocking volcanic rock slabs cambered for drainage, their tight joints resisting water infiltration. This wasn't just stacking materials, it was a masterclass in load distribution and hydrodynamics. Modern tests reveal why these roads endured. Laser scans show Roman surfaces shed water at a 20-degree angle, preventing pothole-causing freeze-thaw cycles. Their aggregate layers channeled groundwater sideways through hidden culverts, a drainage system so effective some still function today. Compare that to our asphalt roads where water seeps through cracks, eroding the base until the surface collapses. The irony, we've known about Roman techniques for centuries. Vitruvius detailed them in his engineering manuals, yet prioritized speed over longevity. But the real secret wasn't just physics, it was foresight. Roman surveyors plotted routes with near-military precision, using Gromer's ancient theodolites to ensure gentle gradients. Curves were calculated to accommodate marching legions, and mile markers placed every 1,000 paces gave birth to the word mile. Some roads included raised sidewalks and horse tracks, anticipating traffic flow like a prehistoric highway engineer. Perhaps the most humbling evidence lies beneath modern cities. When London excavated for its Crossrail project, workers uncovered a Roman road 7 meters underground, its oak foundation piles still intact after 18 centuries of bearing weight. Today's roads, designed for 20-year lifespans, seem almost disposable by comparison. Walking along the Via Appia at sunset, your footsteps echo on stones that carried Caesar's legions, medieval pilgrims, and now tourists with smartphones. The message in those worn grooves is clear. Building to last isn't about better technology, it's about better priorities. When you think of armor, paper probably isn't the first material that comes to mind, unless you're a 10th century Chinese general. During the Tang and Song dynasties, warriors wore suits of armor crafted not from steel or leather, but from hundreds of layers of mulberry paper, bonded with silk and lacquer. This wasn't a desperate improvisation, it was a deliberate innovation, offering protection so effective that some units preferred it over metal. Surprisingly, modern tests show this paper armor could stop arrows and even early bullets, all while weighing less than half of today's Kevlar vests. The secret lay in the physics of layered materials. Each sheet of paper, made from mulberry bark, contained long, interlocking fibers that distributed force like a natural shock absorber. When struck, the layers would flex and compress, dissipating energy across the entire surface rather than concentrating it in one spot. Silk threads stitched between sheets added tensile strength, preventing tears, while rice glue and lacquer made the assembly water-resistant. The result, armor that could absorb the impact of a broadhead arrow, a feat metal plates often failed at, since arrows could wedge between rigid segments. But why paper? For starters, it solved two critical problems: weight and cost. A full set of iron armor could weigh over 60 pounds, exhausting soldiers in prolonged battles, while paper armor rarely exceeded 15. In humid southern China, where metal rusted quickly, paper's resistance to moisture made it a pragmatic choice. There's also evidence that the layered design trapped air pockets, providing insulation against both winter cold and summer heat, something no metal cuirass could offer. Modern military researchers have taken notice. Laboratories recreating paper armor found that 30 layers could stop a 9mm bullet when angled correctly, rivaling early 20th century flak jackets. The silk stitching, it turns out, played a role similar to the aramid fibers in Kevlar, catching and slowing projectiles through friction. Yet, unlike synthetic materials, paper armor was biodegradable and required no industrial processes, just skilled hands and organic materials. The real lesson here isn't just about materials, it's about rethinking what strength means. While European knights clanked around in plate mail, Chinese warriors moved with agility, their armor bending with their bodies rather than resisting motion. Some surviving examples even show decorative painting, proving protection didn't have to sacrifice artistry. In an age where modern body armor strains soldiers' backs and limits mobility, these paper-clad warriors whisper an alternative. Sometimes resilience isn't about hardness, it's about smart design. Long before Charles Goodyear patented vulcanization in 1844, the Maya were crafting bouncy, durable rubber goods that defied nature's limitations. In the steamy lowlands of Mesoamerica, they pioneered the world's first synthetic material, a waterproof, elastic substance so advanced it still puzzles chemists today. Their secret, a mystical-sounding process involving morning glory vines and latex that transformed sticky tree sap into something far more extraordinary. The Maya didn't just harvest rubber, they engineered it. By mixing raw latex from the Castilla elastica tree with juice from the Ipomoea alba vine, they triggered a chemical reaction modern science calls vulcanization. This wasn't mere trial and error. Recent spectroscopic analysis of ancient rubber balls reveals the Maya achieved molecular cross-linking, the same principle behind car tires, by carefully controlling ratios and heat. The vine's sulfur compounds bonded with latex polymers, creating a material that could withstand intense pressure without melting in tropical heat or cracking in drought. Consider their iconic ball game, a ritual so intense players sometimes died from the impact of a 6-pound rubber sphere moving at highway speeds. Spanish chroniclers wrote with awe about how these balls rebounded, as if alive, unlike anything Europeans had seen. Modern replicas confirm their superiority. Maya rubber balls retain bounce and shape better than 19th-century vulcanized versions, thanks to an optimized balance of elasticity and toughness. But their innovation didn't stop at sports. They waterproofed sandals, tools, and even textiles by layering rubberized fabrics, a technique akin to modern rainwear, and created flexible containers that kept liquids fresh without leaching toxins, something petroleum-based plastics still struggle with. The real mystery, how they discovered this process. Unlike old-world civilizations that relied on observable metallurgy or ceramics, the Maya manipulated materials on a molecular level without microscopes or chemistry labs. Some researchers theorize morning glory's ritual use as a hallucinogen led to accidental discoveries, while others point to the Maya's sophisticated understanding of plant synergies. Either way, their rubber proved so valuable it became a form of currency traded across empires. Today, as we grapple with microplastics and disposable synthetics, Maya rubber offers a forgotten lesson in sustainable material science. Their products biodegraded safely yet lasted generations, a stark contrast to our petroleum-dependent world. Laboratories now study their formulas for eco-friendly alternatives, proving sometimes the most advanced solutions aren't found in futuristic labs, but in the wisdom of those who learn to speak nature's chemical language. Along the Nile's fertile banks, where sun and sand conspired to irritate the eyes, ancient Egyptians didn't just wear makeup, they crafted a shield. Their iconic kohl eyeliner, smudged in dramatic almond shapes, wasn't merely about aesthetics. Modern labs have uncovered something startling. Those ebony streaks contained antimicrobial properties rivaling today's antibiotic ointments. While we swipe on mascara loaded with synthetic preservatives, the Egyptians were blending beauty and medicine into a single, elegant stroke. The secret lay in their ingredients. Archaeologists analyzing tomb cosmetics found galena, a lead-based mineral combined with crushed malachite, copper ores, and even animal fats. At first glance, lead sounds alarming, but here's the twist. When processed into fine coal, it triggered a chemical reaction on the skin's surface. Studies show these formulations released nitric oxide, a compound that boosted the immune system's ability to fight eye infections. The copper additions acted as a natural disinfectant, tackling bacteria like Pseudomonas aeruginosa, a common culprit behind blinding trachoma. Even the fat base played a role, creating a barrier against wind-blown sand and flies that carried disease. Compare that to modern eyeliners. Most commercial brands prioritize waterproof longevity over health, using polymers and parabens that can irritate sensitive skin. Some even harbor bacteria if left open too long, a irony the Egyptians avoided by design. Their coal's antimicrobial effects were so potent that researchers at Francis Pierre and Marie Curie University recreated ancient recipes and found they outperformed some antibiotic drops against conjunctivitis. But the brilliance didn't stop at chemistry. The application itself was medicinal. Egyptians stored coal in ornate tubes with slim ivory or wood applicators, designed to massage the lash line as they applied it. This gentle stimulation improved blood flow, reducing inflammation, a technique akin to modern lymphatic drainage treatments. Wall paintings even depict mothers applying coal to children's eyes during flu season, suggesting they understood its preventative role. What's truly humbling is how holistic their approach was. Modern medicine and cosmetics exist in separate aisles, but for the Egyptians, beauty rituals were healthcare. Even their green eye shadows, made from malachite, contained copper compounds that soothed allergies. Walking through the Louvre or British Museum today, those painted eyes staring back from sarcophagi aren't just art, they're a testament to a culture that saw no divide between looking good and staying well. Perhaps the most poignant lesson lies in the remnants themselves. Archaeologists have found coal pots buried with laborers, not just pharaohs, proving this wasn't a luxury, it was universal medicine. In an age where we've traded natural protection for convenience, those ancient vials whisper a question: when did we decide beauty had to come at the cost of our health? Long before silicon chips and programming languages, a Greek inventor named Hero of Alexandria built machines that seemed to possess a life of their own, mechanical servants that poured wine without being touched, automated theaters where puppet actors performed entire plays, and even singing birds powered by nothing but steam and gears. These weren't crude novelties, they were the world's first robots, engineered with a precision that would make modern mechanical engineers pause in admiration. Hero's most famous creation, the Eolipile, might look like a simple brass sphere perched on pipes, but it contained a revolutionary concept: the first recorded steam engine. When heated, steam shot from two opposing nozzles, causing the sphere to spin at dizzying speeds, a principle we now recognize as jet propulsion. But his true genius lay in automata, devices designed to mimic life. Take his mechanical theater, a fully programmed spectacle where tiny figures moved across a stage, triggered by a rotating cylinder studded with pegs, like an ancient version of a punch card computer. Doors opened automatically, miniature ships sailed across tiny seas, and Hercules shot arrows at a dragon, all without human intervention once the system was set in motion. What's startling is how these machines anticipated modern robotics. Hero's automatic servant used a counterweight system to pour wine, then dilute it with water, essentially a programmable drink dispenser. Another device employed a system of ropes and pulleys to open temple doors when priests lit a fire, creating the illusion of divine intervention. These weren't just party tricks, they demonstrated an understanding of feedback loops and automation that wouldn't resurface until the Industrial Revolution. Modern engineers have reverse-engineered Hero's designs and found them astonishingly efficient. His pneumatic systems, which used air pressure to produce sounds like bird calls or thunder, operated with near-silent precision. The gear ratios in his automated puppet shows were optimized to simulate natural movement, something modern animatronics still struggles with when scaling down. And unlike today's robots that rely on replaceable batteries, Hero's creations drew power from gravity, steam, or simple spring solutions that would keep working for centuries with minimal maintenance. The real mystery isn't how Hero built these devices, but why their principles faded into obscurity. Some historians blame the Roman Empire's focus on practical engineering over theoretical pursuits, while others suggest the knowledge was kept secret within temple workshops. Whatever the reason, it took nearly 2,000 years for humanity to reinvent concepts Hero had already mastered. Standing before a reconstruction of his mechanical theater today, watching those tiny figures move with clockwork grace, you realize something profound. Our age didn't invent automation, we simply gave it microchips. The difference between Hero's robots and ours isn't intelligence, but energy sources. His creations whisper a challenge from the past. What could we build if we paired our digital brilliance with the same mechanical ingenuity? While modern cities rely on complex networks of electric pumps and water towers, the Romans perfected a far simpler solution, one that flowed with the quiet certainty of gravity itself. Their aqueducts weren't just water channels, they were masterclasses in hydraulic engineering, delivering millions of gallons daily across impossible distances without a single moving part. Take the Aqua Claudia, stretching 45 miles from Mountain Springs to Rome. Its gradient dropped just 1 foot every 300 feet, a slope so precise modern laser surveys confirm it's accurate to within fractions of an inch over entire mountain ranges. The secret wasn't just in the slope, but in the system's resilience. Roman engineers designed aqueducts with sedimentation tanks to filter debris, venting shafts to release trapped air, and even distribution tanks that acted like prehistoric water meters. Lead pipes, often criticized today, were lined with calcium deposits within months, creating a protective barrier against leaching, but the real stroke of genius. Redundancy. When one aqueduct needed repairs, others could take over seamlessly. Compare that to modern cities where a single pump failure can leave thousands without water. What's truly staggering is their longevity. The Aqua Virgo, completed in 19 BC, still supplies water to Rome's Trevi fountain today. Meanwhile, America's infrastructure report card gives drinking water systems a dismal C-, with a pipe bursting every 2 minutes. The Romans built aqueducts to last centuries. We replace PVC pipes every 50 years. Perhaps the most humbling lesson lies in their construction methods. Without concrete trucks or GPS, surveyors used Corabate's water-filled leveling tools and inverted sighting tubes to maintain gradients across valleys. They bridged gaps with arches that distributed weight perfectly, many still standing without mortar. In Segovia, Spain, the 2-tiered aqueduct soars 90 feet tall on bare granite blocks, carrying water daily since the 1st century. Modern engineers are finally catching up. New gravity-fed systems in developing nations mimic Roman designs, proving low-tech can outperform high-tech. But here's what lingers. Those ancient builders understood water's behavior intimately, crafting channels that harmonized with nature rather than forcing it. Standing beneath the Pont du Gard's triple-tiered arches, hearing water whisper through stone 2,000 years after the empire fell, you realize true progress isn't about complexity, it's about wisdom. Centuries before factories could mass-produce steel, Indian metallurgists were crafting blades so extraordinary they became the stuff of legend, not through brute force, but through an alchemical understanding of fire and iron. Wootz steel, the progenitor of Damascus blades, wasn't just strong. It was a material paradox, combining glass-like hardness with the flexibility of a willow branch. What made it truly irreplaceable was its signature surface, swirling patterns like frozen liquid, revealing microscopic layers of carbide crystals arranged in waves. Even today, with our electron microscopes and atomic-level metallurgy, no one has fully replicated its marriage of beauty and lethal function. The magic began in clay crucibles, where artisans melted iron ore with specific leaves and charcoal in precise ratios. This wasn't random combustion, it was chemistry in action. The carbon-rich plant matter infused the iron with just the right amount of carbon, between 1 and 2%, while trace elements like vanadium from Indian ore deposits created unique molecular structures. After days of slow cooling, the resulting ingots developed cementite nanowire structures so fine they weren't observed again until the invention of electron microscopy in the 1930s. When forged into blades, these nanowires formed the iconic watered silk patterns while giving the steel self-sharpening properties. Every use exposed fresh, ultra-hard carbide edges beneath the surface. Modern attempts to recreate Wootz reveal how much we've lost. Laboratories using spectral analysis found trace elements like tungsten and molybdenum in ancient samples, impurities we now meticulously remove from steel, unaware they contributed to its legendary performance. Even when scientists follow 16th-century Persian manuscripts to the letter, their replicas lack the original's nanostructure, the missing ingredient. Historical accounts describe blades being forged over months, with cycles of folding and annealing that allowed crystals to align perfectly, a luxury our industrial processes can't afford. Perhaps the most astonishing testament to Wootz steel's superiority lies in the accounts of crusaders, European knights accustomed to swords that shattered against chainmail, traded fortunes for Damascus blades that could cleave a floating scarf with a single stroke. The steel's reputation became so mythic that blacksmiths later tried mimicking its patterns through pattern welding, folding different metals together. But these imitations lacked the true Wootz's molecular harmony. What's haunting isn't just the loss of technique, but the loss of philosophy. Wootz wasn't mass-produced. Each ingot was a collaboration between miner, smelter, and smith, with knowledge passed through guilds like sacred lore. Today, as we rediscover the value of slow craftsmanship and material purity, these ancient blades whisper a question: when did we mistake speed for progress and uniformity for perfection? Holding a genuine Damascus sword, you're not just gripping steel, you're holding a millennium of patience, precision, and respect for the elements that modern industry has yet to relearn. Centuries before the Montgolfier brothers became famous for their 18th-century hot air balloons, Chinese inventors were already mastering the skies with paper and fire. As early as the 3rd century BCE, during the Three Kingdoms period, military strategist Zhang used airborne lanterns known as Kongming Lanterns to send signals across battlefields at night. These weren't just floating lights, they were the world's first practical hot air balloons, operating on the same principles that lift modern balloons today. The design was deceptively simple: a lightweight bamboo frame covered with oiled paper, with a small wax or oil flame suspended at the opening. As the air inside heated, it became less dense than the surrounding atmosphere, creating lift. What's remarkable is how precisely ancient engineers balanced these elements. Too large a flame risked igniting the paper, while too small a flame wouldn't generate enough lift. Surviving accounts describe lanterns rising hundreds of feet, drifting for miles before the fuel exhausted, a spectacle that dazzled both armies and emperors. Modern aeronauts would recognize the physics immediately. The Kongming Lantern's buoyancy relies on the ideal gas law, which states that heated air expands and becomes lighter. Unlike today's nylon balloons with propane burners, these ancient versions used renewable materials, biodegradable paper, and plant-based fuels. Some lanterns even featured adjustable flaps to control ascent, proving these weren't just novelties but carefully calibrated flying machines. The most astonishing evidence of their sophistication comes from Tang Dynasty records, which describe ceremonial lanterns carrying small payloads, incense burners, or even poetic messages anticipating future cargo flights by over 1,000 years. During the Ming Dynasty, lantern festivals became so elaborate that some designs reportedly stayed aloft for hours, their colored papers glowing like celestial bodies against the night sky. What's truly humbling is realizing how little the core technology has changed. Modern hot air balloons, from weather probes to tourist rides, still rely on heated air for lift. The main difference: scale and materials. Where ancient Chinese lanterns used fragile paper, we use synthetic fabrics. Where they burned whale oil, we use propane. Yet side by side, the principles remain identical. Perhaps the most poignant legacy of these early flights lies in their cultural impact. Unlike Western aviation pioneers who sought conquest or commerce, the Chinese saw flight as harmony, a union of fire and wind, earth and sky. Today, when you watch a Kongming lantern float into the darkness, you're witnessing more than physics in action. You're seeing a dream unbroken across millennia, a testament to humanity's oldest longing, to rise, however briefly, and touch the stars. In the heart of the Aztec Empire, where towering temples reflected in the waters of Lake Texcoco, an agricultural marvel thrived, one that could teach our modern farms a lesson in sustainability. The Chinampas weren't just floating gardens, they were masterpieces of ecological engineering, producing up to 7 harvests a year without synthetic fertilizers or plows. These rectangular plots, anchored to the lakebed with willow trees and built from layers of mud, aquatic plants, and compost, functioned like nature's own hydroponic system. While today's industrial agriculture depletes topsoil at an alarming rate, the Chinampas actually improved their fertility with every season. Thanks to a self-renewing cycle modern permaculturists are only now beginning to replicate. The secret lay in the water itself. Channels between each Chinampa acted as natural irrigation ditches, while the porous construction allowed nutrient-rich lake water to seep through the roots continuously. Aztec farmers practiced polyculture, planting maize, beans, squash, and flowers together in the same plot, a technique that deterred pests and maximized space centuries before the term companion planting entered agricultural textbooks. Waste from fish and waterfowl fertilized the soil naturally, creating a closed-loop ecosystem where nothing was wasted. Modern soil scientists analyzing Chinampa remnants have made startling discoveries. The layered beds contained higher concentrations of nitrogen and phosphorus than surrounding farmland, with microbial activity rivaling the richest forest soils. Unlike today's monoculture fields that require constant chemical inputs, these floating farms maintained their productivity for centuries through natural processes. Satellite imagery even reveals their ghostly grid patterns still visible beneath Mexico City's urban sprawl, a testament to their enduring design. What's truly revolutionary is how little energy the system required. No diesel-powered tractors, no groundwater pumps, just human labor and an intimate understanding of wetland ecology. The Aztecs even engineered their Chinampas to resist flooding during storms, with willow roots stabilizing the banks like living retaining walls. Compare that to modern industrial farms, where soil erosion costs the global economy billions annually. Perhaps the most humbling lesson lies in scale. At their peak, Chinampas covered over 12,000 hectares and fed an estimated 200,000 people in Tenochtitlan alone, a city larger than any in Europe at the time. Today, urban farmers in Xochimilco still practice traditional Chinampa agriculture, their yields outperforming nearby conventional farms by up to 40%. Standing on these fertile islands, hearing the squelch of rich mud underfoot, you realize something profound. The future of sustainable agriculture might not lie in futuristic vertical farms, but in rediscovering the wisdom of those who worked with nature rather than against it. Beneath the marble floors of the ancient temple of Artemis at Ephesus, hidden from worshippers' eyes, ran a network of clay pipes so advanced it would take 2,000 years for the modern world to catch up to its ingenuity. These weren't just drainage channels, they were the world's first radiators, part of a hypocaust heating system that kept the massive stone structure warm during chilly Mediterranean winters. While we credit the Romans with perfecting underfloor heating, the Greeks pioneered the concept in grand temples like this one, mastering climate control centuries before the advent of thermostats or electric furnaces. The system worked with elegant simplicity. Slaves or servants would stoke wood-fired furnaces in basement chambers, sending hot air through the hollow spaces beneath raised floors and up through vertical pipes embedded in the walls. The clay's thermal properties were key: thick enough to retain heat for hours, yet porous enough to allow gradual radiation. Archaeologists have found that temperatures in heated rooms could reach a consistent 70 degrees Fahrenheit, rivaling modern central heating. What's remarkable is how they balanced airflow. The pipe diameters were carefully calibrated to distribute heat evenly without creating hotspots, while vents at ceiling level allowed cool air to cycle back down for reheating, an ancient precursor to convection systems. Modern engineers have recreated these systems with surprising results. When a team restored a hypocaust in a Roman villa in Britain, they discovered the clay pipes maintained heat so efficiently that just 2 firings per day sufficed. Compare that to today's forced air systems, which constantly burn energy to compensate for heat loss through thin ductwork. The secret lay in the thermal mass of those clay pipes, which continued radiating warmth long after the fires died down, something our lightweight metal ducts can't replicate. But the Greeks didn't stop at floors. In wealthier homes and public baths, they extended the system to warm benches and even beds through terracotta heat boxes. The Olynthus house excavations revealed sophisticated valve systems that let residents control heat room by room, much like modern zoning. Some pipes were deliberately coiled to increase surface area, proving they understood principles of heat exchange we'd later formalize in thermodynamics equations. What's truly humbling is realizing how much energy we waste reinventing what ancient architects already perfected. Today's radiant floor heating, hailed as a modern luxury, operates on nearly identical principles, just swapping clay for plastic tubing and wood fires for gas boilers. The main difference: our systems last decades. The Ephesus pipes functioned for centuries. Standing in the shadow of those crumbling temple walls, you can almost feel the whisper of warm air that once flowed through them, a reminder that true innovation isn't always about new technology, but about refining the brilliant solutions already beneath our feet. At noon in ancient Thebes, when the sun cast no shadow, a simple stone slab marked with precise lines became Egypt's most reliable clock. These weren't the decorative sundials we see in gardens today. They were sophisticated timekeeping instruments, dividing daylight into 12 equal hours centuries before mechanical clocks existed. What's astonishing isn't just their accuracy, but how they compensated for Earth's tilted axis, a feat requiring astronomical knowledge we often assume came much later. The earliest Egyptian sundials, like the one found in the Valley of the Kings dating to 1300 BCE, used a raised gnomon to cast shadows across curved hour lines. But here's what set them apart: these lines weren't spaced evenly. The Egyptians understood that the sun's path changes with the seasons, so winter hours with shorter daylight were marked closer together than summer hours. Some temple dials even had adjustable gnomons for different latitudes, proving these were tools for professionals, not just casual time tellers. Modern recreations show they could track time within 15-minute accuracy, comparable to early mechanical clocks of the Middle Ages. What's truly groundbreaking is how they standardized timekeeping without gears or weights. The Cairo Museum houses a portable sundial from Tutankhamun's era with a built-in plumb bob to ensure perfect leveling anywhere. Another discovered near Luxor features a dual scale system, one side for civil use, another for tracking sacred festival dates based on star alignments. This wasn't just measuring hours, it was synchronizing an entire civilization's rhythm with celestial movements. The secret to their precision lay in meticulous observation. Temple astronomers spent generations recording the sun's solstice and equinox positions, etching their findings into stone, shadow tables that functioned like prehistoric ephemerides. Some sundials incorporated notches to account for atmospheric refraction, the bending of sunlight near the horizon, a phenomenon European scientists wouldn't document until the 17th century. Today's atomic clocks may outpace them in raw precision, but Egyptian sundials achieved something modern technology often neglects: harmony with natural cycles. Their hours stretched and contracted with the seasons, keeping humans aligned with daylight's ebb and flow. In an age where digital screens disconnect us from the sky's rhythms, these stone timekeepers whisper an invitation to look up and remember time was never meant to be imprisoned in ticking hands, but to dance with the sun. In the shadow of the Colosseum, where gladiators bled for sport, Roman doctors were performing medical miracles with tools so precise they wouldn't look out of place in a modern operating room. Archaeologists excavating Pompeii's House of the Surgeon uncovered bronze scalpels with interchangeable blades, bone drills with screw-like tips for controlled penetration, and uterine forceps nearly identical to those used today, all crafted 2,000 years before anesthesia or germ theory. What's shocking isn't just their appearance, but how little our core surgical instruments have evolved since. A 1st century Roman healer's toolkit contained over 200 specialized devices, from rectal speculums to cataract needles, proving ancient medicine was far more sophisticated than we often assume. The star of this collection was the lenticular, a double-ended scalpel with a spoon-shaped tip for precise incisions and a blunt edge for probing wounds. Modern surgeons testing replicas found its balance and weight distribution rival high-carbon steel scalpels, while the slight curvature allowed cleaner cuts with less tissue damage. But the real stroke of genius lay in the materials. Roman instruments were often made from a copper-silver alloy called Corinthian bronze, which naturally inhibited bacterial growth, an accidental antimicrobial property that likely saved countless lives. Some tools even featured collapsible designs for portability, like a field medic's kit ready for battle. Perhaps most impressive were their bone drills. The Roman terebra had a tapered spiral tip that allowed gradual penetration without splintering, identical in principle to today's orthopedic drills. Archaeologists found one buried with a surgeon in Rimini, its fluted grooves still sharp enough to pierce fresh bone in experimental tests. These weren't crude implements, they were engineered for specific procedures, with variations for trepanning skulls or setting fractures. But tools alone don't tell the full story. Scrolls from Alexandria's medical school describe procedures these instruments facilitated, from cataract couching, pushing clouded lenses aside with a needle, to lithotomy, bladder stone removal, with survival rates matching 18th century outcomes. The Romans pioneered early cesarean sections, using hooked knives to minimize bleeding, and treated hernias with specialized trusses that wouldn't be improved upon until the Renaissance. What's truly humbling is realizing how much knowledge was lost. Galen's writings detail sterile techniques like boiling instruments and using vinegar washes, practices ignored during the Middle Ages. A 1st century nasal speculum from Pompeii features a scissor-like mechanism still used in ENT clinics today, yet it took until the 19th century for Western medicine to rediscover its design. Holding one of these ancient tools, you're struck by a sobering thought. For all our MRI machines and robotic surgery, the hands of a skilled healer wielding well-crafted steel remain medicine's most timeless technology. Long before satellites and GPS signals, Chinese navigators held the Earth's secrets in the palm of their hands, a simple spoon-shaped lodestone balanced on a polished bronze plate. These first compasses, called Sinan, didn't just point north, they unlocked the planet's invisible magnetic fields, revolutionizing exploration in ways we're still unraveling today. What's astonishing isn't just their invention, but how quickly they transformed from mystical curiosities to indispensable tools that reshaped the world map. The genius of these early compasses lay in their elegant simplicity. Craftsmen carved lodestone, a naturally magnetic mineral, into the shape of a celestial spoon, its handle always aligning with the Earth's magnetic poles when placed on a smooth surface. By the Song dynasty in the 11th century, they'd refined the design into floating needles magnetized by rubbing them against lodestone, a technique so effective that modern hikers still use nearly identical methods to magnetize emergency compass needles. But here's what set Chinese navigators apart. They didn't just follow the needle's direction, they interpreted its subtle dips and wobbles to account for magnetic declination, the difference between true north and magnetic north. Marco Polo marveled at this in his journals, describing Chinese sailors correcting their course with adjustments no European navigator yet understood. The global impact was seismic. Imagine Arab traders carrying compass knowledge along the Silk Road to the Mediterranean, where it supercharged Venetian and Genoese shipping. Picture Zhang, his massive treasure fleet, some ships over 400 feet long, relying on compasses to navigate the Indian Ocean with pinpoint accuracy, a century before Columbus stumbled upon the Americas. While European explorers clung to coastal hugging for fear of losing their way, Chinese and later Portuguese sailors struck out across open oceans, their compasses whispering the Earth's hidden language. Modern digital compasses might seem light years ahead, but strip away the electronics and the core principle remains unchanged. Your smartphone's compass app still relies on magnetometers detecting Earth's magnetic field, just like those Song dynasty needles. The real difference: ancient compasses required no batteries, no software updates, and could survive typhoons that would fry today's devices. Archaeologists have found Ming-era compasses submerged for centuries that still point true after drying, their lodestones retaining magnetism like a celestial memory. What's truly humbling is realizing how much we've lost in translation. Traditional Chinese compasses weren't just tools, they were cosmological models with circular plates marked not just with directions but with 24 solar terms and astrological symbols. Navigators read them like poets decoding the universe, seeing ocean currents and seasonal winds in the interplay of markings. Today, as we stare at blinking GPS dots, we've gained precision but sacrificed a dialogue with the planet that those ancient sailors knew intimately. Holding a replica Sinan, feeling its weight settle into alignment, you're not just holding history, you're holding a conversation with the Earth itself, one that began over 1,000 years ago and still hasn't ended. In the scorching plains between the Tigris and Euphrates rivers, where civilization first took root, a simple wooden tool changed humanity's destiny forever: the Mesopotamian plow. Unlike today's roaring tractors with GPS-guided systems, these early implements were little more than sharpened branches dragged by oxen, yet they unlocked something extraordinary: the ability to domesticate the earth itself. What's astonishing isn't just their age, dating back to 6000 BC, but how their fundamental design still underpins modern agriculture, proving sometimes the oldest solutions are the most enduring. The genius of these plows lay in their adaptability. early versions, called ards, were essentially curved sticks that scratched furrows into the soft alluvial soil. But by 3000 BC, Sumerian farmers had added a critical innovation, a bronze or iron tip called a share, which could slice through tougher ground. Unlike modern plows that flip soil completely, these ancient tools worked more like surgical instruments, gently parting the earth to preserve moisture in arid climates. Archaeologists studying cuneiform tablets have found detailed instructions for plow maintenance, revealing how seriously Mesopotamians took this technology. Some texts even list plows among a city's most valuable assets, alongside temples and granaries. Fast forward to today, and the parallels are startling. While our tractors are faster, the basic mechanics of breaking ground remain unchanged. The modern moldboard plow, the curved metal blade that turns soil, still mimics the shape and angle of Mesopotamian designs. Even no-till farming, hailed as a 21st century innovation, echoes ancient techniques where minimal soil disturbance preserved fertility. The main difference. Scale and speed. Where an ox-drawn plow might till 1 acre per day, today's machines cover 50, but at a cost. Industrial farming has degraded 33% of the world's topsoil in just the last century, while Mesopotamian fields remained productive for millennia. What's truly revolutionary is how these plows transformed society. Before their invention, humans were hunter-gatherers roaming for food. The plow anchored them to the land, enabling surplus crops that birthed cities, trade, and written records to track harvests. Some historians argue the plow's efficiency even altered gender roles. As muscle-powered farming shifted labor divisions, a social impact as profound as its agricultural one. Yet the most humbling lesson lies in the details. Modern agronomists studying ancient fields near Ur have found something remarkable. Alternating crop patterns and plow marks suggesting deliberate contour farming to prevent erosion techniques we now consider cutting-edge sustainable practice. Walking through the British Museum's collection of cuneiform ploughing manuals, you realize something profound. 6,000 years ago, farmers understood something we're still relearning, that working with the land, not against it, is the true foundation of civilization. Gliding silently across northern lakes, the birchbark canoes of Native American tribes were marvels of hydrodynamics centuries before engineers coined the term. While European explorers struggled with heavy oak vessels that sat low in the water like floating logs, these indigenous crafts sliced through waves with the grace of a diving loon, some reaching speeds over 10 miles per hour with just paddle power. The secret wasn't just in the materials, but in a shape so perfectly adapted to freshwater travel that modern canoe designers still use it as their gold standard. At first glance, the construction seems impossibly delicate sheets of birch bark stitched together with spruce roots and sealed with pine pitch, stretched over a lightweight cedar frame. Yet this combination created a hull both feather-light and astonishingly strong. The bark's natural waterproofing resisted rot, while its flexibility allowed the canoe to absorb impacts that would splinter rigid wooden boats. But the real breakthrough was the hull's shallow arch design, forming a cross-section like a flattened oval. When tilted slightly on its side, a technique called leaning or edging, the shape generated hydrodynamic lift, reducing drag by up to 40% compared to flat-bottomed European boats. Modern fluid dynamics simulations confirm what indigenous builders knew intuitively. That subtle curve prevented the suction effect that slows conventional hulls, allowing the canoe to glide forward with each paddle stroke rather than fighting the water. What's truly revolutionary is how these designs adapted to specific environments. The Algonquin tribes perfected a low-profile version for river rapids, with a rounded bottom that spun on a dime, while the Ojibwe built wider, stable models for Great Lakes fishing that could handle 3-foot waves. Some Pacific Northwest canoes featured dramatic upswept bows to cleave through ocean swells, anticipating the wave-piercing hulls of modern racing boats. European explorers were so impressed they commissioned native builders to make canoes for their expeditions. Lewis and Clark's Corps of Discovery relied on them to traverse the continent. Today's Kevlar and carbon fiber canoes may be lighter, but they're essentially high-tech copies of those ancient templates. Naval architects still refer to the Indian curve, that critical midsection profile first developed by indigenous builders when designing recreational canoes. The only significant modern innovation, replacing spruce root lashings with epoxy, though some traditionalists argue this makes repairs harder. Perhaps the most humbling testament to their brilliance lies in competitive racing. During the 1990s, a team of MIT engineers spent millions developing a perfect racing canoe using computational fluid dynamics. When tested against a traditional birchbark replica built by Maine's Penobscot tribe, the high-tech model was barely 3% faster, a margin easily erased by the skill of an experienced paddler. Holding a strip of birch bark against your palm, feeling its paper-thin strength, you begin to understand the deeper lesson. True innovation isn't about forcing nature to conform to our tools, but shaping our tools to honor nature's wisdom. Imagine an instrument so perfectly balanced it could make warriors weep and philosophers pause mid-argument. The Greek lyre wasn't just a tool for music, but a masterpiece of acoustic engineering. Crafted from tortoise shells, antelope horns, and gut strings stretched over a carefully calibrated wooden frame, this ancient harp-like instrument produced tones so pure they became the foundation of Western music theory. Modern luthiers have spent centuries trying to replicate its resonance, yet even Stradivarius, the legendary violin maker, couldn't match the harmonic complexity achieved by unknown artisans in 5th century Athens. The magic began with materials chosen for their vibrational qualities. Lyre makers selected tortoise shells not just for their curvature, but for the way their collagen-rich structure amplified sound naturally, a property modern synthetics still can't duplicate. The strings, made from sheep intestines cleaned and twisted under tension, produced a warm, organic timbre that metal or nylon strings struggle to emulate. But the real genius lay in the proportions. Surviving lyres from Pompeii show mathematical precision in their design. The distance between the bridge and soundbox matched the harmonic ratios Pythagoras discovered, creating perfect octaves and fifths without a single electronic tuner. What's truly astonishing is how versatile these instruments were. A skilled player could evoke the thunder of Zeus with deep, rhythmic strumming or mimic the whisper of olive leaves with delicate finger plucking. The lyre's 7 strings tuned to the ancient Dorian mode could accompany epic poetry, lead drinking songs, or even simulate the sounds of nature during religious rituals. Modern synthesizers might recreate these tones digitally, but they lack the physicality of a lyre's sound waves vibrating through wood and bone, something recordings can never fully capture. Recent experiments by the University of Crete reveal why. Using laser vibrometry to analyze replica lyres, researchers found the instrument's soundbox vibrated at multiple frequencies simultaneously, creating a 3-dimensional sound that enveloped listeners. Compare that to today's speakers, which project sound linearly. The lyre's tones also carried unusually well in open-air amphitheaters, thanks to its broad frequency range, an accidental benefit of materials chosen for durability rather than acoustic science. Yet the most profound legacy of the lyre isn't technical, it's cultural. This instrument shaped the very concept of music as both art and science. Plato argued its harmonies could calibrate the human soul, while Spartan generals used lyre music to coordinate troop movements in battle. Walking through the ruins of Delphi, where priestesses once played lyres to channel prophecies, you realize something haunting. We've gained infinite digital soundscapes, but lost the intimacy of music crafted from living materials, where every note carried the memory of the animal, plant, and human hands that made it sing. Buried beneath the volcanic ash of Pompeii or resting undisturbed in ancient shipwrecks, Roman glass glows with an otherworldly clarity, some pieces so pristine they could be mistaken for modern crystal. What's astonishing isn't just their survival over 2,000 years, but how they defy one of glass's greatest weaknesses, brittleness. While today's wine glasses shatter from a careless knock, Roman vessels have endured earthquakes, shipwrecks, and the weight of centuries without losing their luster. The secret lies in a forgotten alchemy of minerals and craftsmanship that modern factories have yet to fully replicate. Roman glassmakers worked with two key advantages we've since abandoned: patience and impure materials. Their primary ingredient, sand from the Levant coast, contained trace amounts of manganese and antimony, contaminants by today's standards, but magic ingredients in antiquity. When fired at temperatures around 1,000 degrees Celsius, these impurities reacted to create a glass that was slightly blue or green tinted but remarkably stable. Modern X-ray fluorescence tests reveal the real genius. The manganese acted as a decolorizer, neutralizing the iron oxide that typically gives ancient glass a cloudy appearance, while the antimony increased durability by strengthening the molecular structure. The real breakthrough, though, was in their cooling techniques. Unlike today's tempered glass that's cooled rapidly for hardness, Roman artisans practiced annealing, a slow, days-long cooling process that relieved internal stresses. Some luxury pieces were reportedly cooled underground in specially dug pits where temperature fluctuations were minimal. This painstaking method prevented the microscopic fractures that plague modern glass, giving Roman pieces their legendary resilience. The famous Portland vase, a 1st century masterpiece, demonstrates this perfectly. Its delicate cameo glass has survived intact despite being dropped, stolen, and even deliberately smashed by a museum visitor in 1845. But here's what stumps material scientists. Some Roman glass exhibits a peculiar iridescence, not from decay but from an intentional surface treatment. Analysis suggests they used vinegar or urine to create thin mineral layers that diffracted light, an early form of nanotechnology. The Lycurgus cup, which changes color from red to green depending on lighting, uses gold and silver nanoparticles to achieve this effect, a technique we only rediscovered in the 1950s with the development of dichroic glass. The tragic irony: we've known the basics of Roman glassmaking since Pliny the Elder described it in his Natural History, yet industrialized production favors speed over longevity. Our soda-lime glass is cheaper to produce and more uniform, but lacks the chemical stability of its ancient counterpart. Laboratories studying Roman glass formulations have created modern versions with similar durability, but the energy-intensive annealing process makes them economically unviable for mass production. Perhaps the most poetic testament to Roman glass lies not in museums, but in the Mediterranean itself. Beachcombers still find sea glass pebbles, broken Roman vessels tumbled smooth by waves over centuries. These fragments retain their vibrant blues and greens while modern glass turns frosted within decades. Holding one, you're touching more than history. You're holding a material that outlasted empires, a testament to an era when craft wasn't measured in output but in endurance. In a quiet Tang dynasty alchemy lab around the 9th century, a mixture meant to grant immortality instead birthed the very force that would shatter medieval warfare forever. Chinese alchemists blending saltpeter with sulfur and charcoal stumbled upon an unexpected result: a flash, a roar, and a cloud of smoke that left their clay crucibles in fragments. This wasn't the elixir of life they sought, but something far more transformative: gunpowder, the world's first chemical explosive. What began as a failed quest for eternal youth became the catalyst for sieges, revolutions, and ultimately, the modern world's balance of power. The earliest recorded formula appears in a Taoist text from the year 850, warning ominously that mixing these ingredients with certain metals produced flames capable of scorching beards and burning down houses. At first, the discovery was harnessed for spectacle. Elaborate fireworks lit the skies during imperial celebrations, their colored smoke believed to scare away evil spirits. But by the Song dynasty, military engineers saw potential far beyond ceremonial use. They packed the powder into bamboo tubes reinforced with iron bands, creating the earliest flamethrowers and grenades. These fire lances could spew flames over 15 feet, while primitive bombs filled with shrapnel and poison gases were hurled from catapults at enemy fortifications. What made gunpowder revolutionary wasn't just its destructive power, but its portability. Unlike Greek fire, which required complex delivery systems, gunpowder weapons could be deployed by a single soldier. The Mongols, who acquired the technology through conquest, spread it across Eurasia with terrifying efficiency. By the 13th century, Arab chemists had refined the formula into finer grains for more controlled explosions, while Europeans, initially baffled by the devil's thunder, eventually scaled it into cannons that toppled castle walls. The age of chivalry ended not with a sword stroke, but with a flash of Chinese alchemy. Modern explosives like TNT or C4 may be exponentially more powerful, but none match gunpowder's historical impact. Its invention shifted warfare from muscle and steel to chemistry and engineering, rendering armored knights obsolete and giving rise to centralized nation-states that could afford standing armies. Yet the cruelest irony lies in its origins. A substance born from the pursuit of life's prolongation became history's great accelerator of death. Today, as we watch fireworks paint the night sky, we're witnessing the same chemical reactions that once redrew the map of the world, a reminder that discovery rarely follows the path we intend. While sundials ruled the day, ancient Egypt's greatest timekeeping innovation flowed in the dark, literally. In the shadowy corridors of temples and the private chambers of nobles, water clocks measured night hours with astonishing precision, turning something as simple as a dripping vessel into history's first mechanical timer. Unlike modern clocks with their gears and circuits, these clepsydræ relied on gravity and hydraulics, proving that sometimes the most elegant solutions emerge from watching a river rather than fighting it. The genius of these devices lay in their deceptive simplicity. A basic water clock was just a stone or alabaster bowl with a small hole near the base, filled to a marked line at sunset. As water trickled out, interior hour lines, often adjusted seasonally, tracked the passage of time. But the most sophisticated versions, like the one found in Amenhotep Roman III reign, were multi-chambered masterpieces. These clocks used a series of interconnected containers to maintain constant water pressure, ensuring the flow rate stayed even as the upper vessel emptied. Imagine a 14th century BCE version of precision engineering, where priests could measure hours within minutes of accuracy, all without a single moving part. What's truly groundbreaking is how they compensated for Earth-shifting seasons. Egyptian water clocks featured adjustable hour scales, longer lines for winter nights when darkness lasted longer, shorter for summer. Some even incorporated conical shapes to counteract the natural slowing of flow as water levels dropped, a principle later formalized by Bernoulli's equations. The Temple of Karnak housed a massive clepsydra that synchronized rituals across cities, its regulated drips echoing like a metronome for an entire civilization. Modern experiments reveal their startling accuracy. When the British Museum recreated a new kingdom water clock using original diagrams, it kept time within 15 minutes over 12 hours, rivaling medieval mechanical clocks. Unlike sundials, these worked in any weather, underground or on moving ships. Greek historian Herodotus marveled at how Egyptian water clocks could measure even the hour of a man's death with eerie consistency. Yet the real innovation wasn't just in telling time, it was in segmenting it. These clocks divided nights into 12 equal parts, laying the foundation for our 24-hour day. The very word hour traces back to the Egyptian WNWT, the measure of water that filled a clepsydra's chamber. Today, as we obsess over atomic clocks and nanosecond precision, there's something humbling about a technology that turned the patient drip of water into the heartbeat of history. Buried in the frozen soils of Scandinavia and the riverbanks of Eastern Europe, Viking warriors carried a weapon so advanced it seemed forged by gods, not men. The Ulfberht Swords, marked with that mysterious name inlaid in steel, weren't just better than other medieval blades, they were centuries ahead of their time. Imagine a battlefield where most swords bent or shattered like brittle twigs, while an Ulfberht could slice through armor and still retain a razor edge. These weren't mass-produced tools, they were masterpieces of metallurgy, crafted from steel so pure it wouldn't be matched until the Industrial Revolution. The secret lay in their composition. While typical Viking swords were made from bloomery iron, a crude mix of iron and slag that resembled steel more in name than quality, Ulfberhts contained carbon levels near perfect for a sword, around 1.2%. Modern spectrographic analysis reveals this wasn't just good luck. It was deliberate crucible steel, a material so refined it had to be melted at temperatures exceeding 3,000 degrees Fahrenheit. That's hotter than most medieval forges could achieve, suggesting techniques lost to history or possibly imported from distant lands. The steel's purity gave it flexibility and strength in perfect balance, able to flex under stress without cracking, then snap back to true like a tempered spring. But here's what baffles historians: the origin of this steel. Chemical fingerprints trace some Ulfberhts to Central Asia, where Islamic smiths were known to produce high-quality crucible steel under the name Damascus steel. Yet how did these ingots travel thousands of miles to Viking hands? Trade routes, raids? The answer might lie in the Volga River trade networks, where Norse traders exchanged furs and amber for silver, and possibly these prized steel bars. Some Ulfberhts even contained trace metals like vanadium, found only in specific Persian mines, adding layers to an already sprawling mystery. The sword's construction was just as revolutionary. X-rays of surviving blades show a distinctive pattern welding technique, where rods of pure steel were twisted, folded, and hammered into a core, then edged with ultra-hard steel. This created a blade that was both resilient and deadly sharp, a far cry from the uneven, slag-riddled weapons most fighters wielded. Modern blacksmiths attempting to recreate Ulfberhts using period-accurate tools report it takes over 400 hours of labor per sword, explaining why only the wealthiest warriors could afford them. Perhaps the most haunting detail is the name itself, Ulfberht. Inscribed in Latin letters on over 170 swords found across Europe, it's likely a maker's mark. But was Ulfberht a single genius smith, a guild, or even a family passing down secrets for generations? The quality remained consistent across centuries, hinting at tightly guarded knowledge. By the 13th century, the name disappears from history, possibly lost to plague, war, or the very secrecy that protected the craft. Today, holding an Ulfberht feels like touching a paradox. Its steel gleams with a mirror finish even after a millennium buried underground, while modern replicas forged in electric furnaces struggle to match its endurance. In an age where we've mapped the human genome and split the atom, these swords whisper a humbling truth. Some ancient innovations refuse to be outdone, their secrets still buried as deep as the Viking graves that hide them. When Byzantine warships closed in on enemy fleets, their most feared weapon wasn't a battering ram or volley of arrows. It was a hollow bronze tube that breathed liquid hell. The Greek fire syringe, often overshadowed by its more famous cousin, the stationary siphon, was history's first handheld flamethrower, capable of spraying jets of flaming chemicals over 30 feet with nightmarish precision. Unlike modern flamethrowers weighed down by fuel tanks and ignition systems, this ancient terror was elegantly simple. A piston-driven pump mounted on a wooden stock, its barrel preheated to instantly ignite the viscous fuel as it erupted forward. Sailors could sweep decks clean of enemy crews in seconds or turn approaching boarding parties into screaming torches, all without ever leaving their ship's railings. What made this weapon revolutionary wasn't just its destructiveness, but its psychological warfare. Imagine the horror of medieval sailors, accustomed to sword clashes and arrow storms, suddenly facing a weapon that made water itself burn. Historical accounts describe Byzantine marines firing horizontal streams of fire that clung to victims like napalm, while specialized units used curved nozzles to arc flames over shield walls. The fuel's exact composition remains lost, but reconstructions using ingredients mentioned in fragmented texts, pine resin for stickiness, quicklime for spontaneous ignition, create flames that water only intensifies, just as described in terrified Arab chronicles. The military advantage was staggering. During the siege of Constantinople in 717, these syringes turned the tide against a massive Umayyad fleet, their flames reflecting off the Golden Horn's waters like a scene from apocalyptic visions. Unlike Greek fire projectors mounted on ships, which required careful positioning, the syringe's portability allowed defenders to repel boarders from any angle. Some versions reportedly had adjustable nozzles, switching between concentrated streams for precision and wide sprays for area denial, features modern flamethrowers wouldn't replicate until World War II. Yet the real genius lay in its limitations. Byzantine engineers understood that terror loses its edge if overused. Surviving manuals indicate syringes were deployed sparingly, often at decisive moments to maximize shock value. Crews underwent rigorous training to prevent misfires, a real risk given the weapon's volatile fuel, and each syringe team included a dedicated fire guard with wet hides to smother accidental blazes. This wasn't just a tool, it was a psychological scalpel, carefully wielded to break enemy morale without sacrificing tactical surprise. Modern flamethrowers may have longer range and safer ignition systems, but they lack the original's brutal elegance. Watching a reconstruction in action, the hiss of pressurized fuel, the sudden whoosh of a firestorm lighting up the night, you realize something unsettling. For all our drones and smart bombs, few weapons have ever matched the primal fear of watching a man point a metal tube and summon the inferno with a single thrust of his arm. The Greek fire syringe didn't just burn ships, it seared itself into the nightmares of an era, proving that sometimes the most advanced weapon isn't the one with the most gears, but the one that turns courage to ashes in an instant. From unbreakable concrete that heals its own cracks to Damascus steel blades with molecular structures we still can't fully replicate, these 30 ancient marvels reveal a startling truth: our ancestors, weren't just primitive precursors to modern technology. They were master engineers, alchemists, and visionaries whose solutions to timeless problems often surpassed our own. Think about that Roman concrete stronger after 2,000 years than our mixes after 50, or the Inca masonry walls that outlast earthquakes while our skyscrapers rely on costly shock absorbers. These aren't just historical curiosities, they're wake-up calls written in stone, metal, and ingenious design. What's truly humbling is realizing how much knowledge slipped through the cracks of time. The Antikythera Mechanism's celestial calculations, the self-cooling Persian Windcatchers, the Maya's vulcanized rubber, these breakthroughs weren't lost to some apocalyptic event, but to the slow erosion of forgotten craftsmanship and misplaced priorities. We replaced endurance with expedience, trading the Pantheon's eternal dome for buildings with planned obsolescence. Yet as modern scientists now scour ancient texts and artifacts for clues, we're beginning to see the outlines of a different technological path, one where progress meant perfecting rather than replacing, where tools were partners to nature rather than conquerors of it. This isn't about nostalgia or rejecting modernity. It's about recognizing that innovation isn't a straight line forward, but a vast web where past and future constantly converse. Laboratories from MIT to Kyoto are now studying these ancient technologies not as relics, but as blueprints reverse engineering Roman concrete for seawalls against rising oceans, analyzing Damascus steel for next-generation surgical tools, even adapting Inca seismic principles for earthquake-resistant cities. The most exciting discoveries may still lie ahead, hidden in plain sight within these time-tested designs. So as we marvel at smartphones and AI, let's also pause to appreciate the quieter genius of a Viking Sunstone or a Chinese Seismoscope, tools that solved profound challenges with elegance rather than excess. They challenge us to rethink what advanced really means. Was it the Roman aqueduct still flowing after millennia, or our leaking municipal pipes, the Greek fire that burned on water, or the modern flame retardants that fail under mild heat? The answers might surprise you. Now we'd love to hear your thoughts. Which of these ancient technologies left you most awestruck? The precision of Egyptian drill holes, the musical purity of the Greek lyre, or perhaps something we didn't cover? Drop your favorites in the comments below. We read every one. And if you've enjoyed this journey through forgotten brilliance, hit that subscribe button to join us as we keep unearthing history's most extraordinary secrets. After all, the past isn't just behind us, it's waiting to be rediscovered.